Rightio, let's get stuck into the very last bit of our bit on periodicity for HL and looking at transition metal complexes and why they are so brightly coloured. So as we've mentioned, transition metal complexes form coloured. They have compounds that contain electronic energy levels that when we see transitions of the electrons, these fall onto the range of visible light. So therefore that they display a color when we look at them. This is similar to the colors that we saw in the flame colors way back in ECP 20 a long time ago. So in terms of the compounds of D-block metals, though, these are frequently colored both in the solid state and in hydrated solution. You'll remember that copper 2+, we're very familiar with that being blue when it is in aqueous solution. However, copper complexes tend to be uncolored when they're not in water. Okay, so the presence of those water ligands give it the blue color. So let's have a look at why these colors arise. The transition metal colored complexes will change depending on what the ligands are. You can see here that the hexa aqua iron 3 complex will have a yellow color, whereas the hexacyano complex is red. For copper, the CuCl4 complex is yellow, and we see other colors such as pale blue and royal blue when we change those to a mixture of water or water and ammonia ligands. Unlike many transition metal complexes, the silver ammonia complex is colorless. Cobalt complexes can be pink, there's even blues, and violets and greens, and then there's a whole range of colors that we see with nickel and vanadium complexes as well. You may remember from your electromagnetic spectrum that white light is composed of a range of colors from red to violet. So when the light hits an object, some is absorbed and some is reflected. Some is transmitted through if it's transparent. What we see when we observe an object is the result of the colors being removed from the white light and then reflected back to our eye. So for a green object, white light comes in, all the other colors are absorbed, and the green light is reflected. Okay, so the color that is observed is the complementary of the colors that have been absorbed. In your data booklet, you actually have a black and white version of the color wheel, which lists the wavelengths and the colors so that you are able to say what color something would be if you're told what is absorbed, or if you're told what the color is, be able to say what colors are being absorbed. So if something appears yellow, then it is the opposite, the blues and purples, which are being absorbed. If it appears green, then it is the purples and reds that are being absorbed. And if it appears red, then it's the blues and greens that are being absorbed. So the way that complexes form, as we saw, the different ligands cause different colors. So the way that complexes form influences the color of the complex. The d orbitals of a transition metal ion, okay, that is formed dative bonds with the ligands, are affected by the nature of the ligand. Repulsion occurs between the non-bonding electrons of the ligand and the electrons in the d orbital of the transition metal. That repulsion can cause changes in energy. So instead of being the same energy, the orbitals are now split into two groups, lower energy orbitals and higher energy orbitals. If we look at this picture here, we see that we have the energy, white light, yellow and green light is absorbed, causing the electron to rise up, and the solution will appear purple because of the yellow-green absorption. The difference in energy here of this transition is what we're talking about being influenced by the binding of the ligands. Okay, so when we have different binding of different ligands, we see different splitting of these d orbitals between the occupied and non-occupied orbitals. So the amount of energy needed for the transition corresponds to the frequency of radiation within the visible light spectrum, the same as what we saw when we were talking about electron transitions within an atom. The colour shown by the ion is a mixture of the complementary colour of the radiation that is transmitted for that transition. So the formation of the coloured compounds to happen, the ion must have a partially filled 3D orbital. It needs to have unpaired electrons. So as with many of the properties of transition metals, it is all based on unpaired electrons. If it doesn't have unpaired electrons in the 3D subshell, then it will not appear coloured. So if you had your electrons in your diagram here, okay, they have 5D orbitals, all of which have the same energy. But in most of their compounds, these equivalent energy levels are split into 2 or 3 different sets of energy with some orbitals on each level. Okay, so instead of all being the same, they are split. We get d orbital subshell splitting, i.e. some of the d orbitals end up in a higher or lower energy compared to each other. Okay, the splitting of this 3D subshell into more than one level is caused by the ligands and the effect of their electron clouds. This repels the electrons in the d subshells. Okay, so you would get repulsion of these electrons between these electrons and the ligands. Okay, and as a result, the ligand electrons push the orbital closest to them to the energy levels higher than the other energy levels. So we get this split. They are non-equivalent, and we refer to this as field splitting. When we look at the things that can affect the splitting of the d orbitals, they split depending on how close the ligand can get to the ion. So the closer the ligand can get to the metal ion in the center, the greater the repulsion between the non-bonding electrons, and the further apart the d orbitals will split, increasing the energy gap between them. So there are 2 factors that are involved in what we see in this field splitting. The charge on the metal ion, okay, so an ion with greater charge will attract the ligands more strongly than one with a smaller charge, so the ligands will be brought closer. And the overall size of the ligand, okay, this goes back to the idea of steric hindrance. If we have a large bulky ligand, it physically won't be able to get closer, so smaller ligands are able to get closer to the metal ion. The color of the transition metal complex will depend on the number of d electrons in the metal ion and the effect of this repulsion. Okay, they have different number of 3d electrons resulting in different field splitting. The number of ligands that are around the ions as well, and the nature of those ions influence the shape of the complex ion and the colors that we see. You can see here that we have the Cl is going to have a smaller influence than the water, which is smaller than the ammonia, which is smaller than the cyano ligand when we see our splitting effects. It's key to remember that not all d block metal complexes are colored. As we said, if it doesn't have a d orbital, unpaired d orbital electrons, or it's full, there's going to be no color. We can see here with the copper 1+ ion, this will be colorless in complexes because the 3d subshells are all full. In contrast, the titanium 4+ ion is colorless because it has lost all its 3d electrons. So again, there is no 3d electrons here to see the effects of the 3d subshell splitting. An empty or full 3d subshell does not mean that complexes can't form, it just means that they will be colorless. We can see this with the tetrahydro oxo-zinc, where we have the hydroxide ions acting as ligands. So this would be a zinc 2+, the 4- hydroxide giving it a 2- overall. So we see the formation of a complex ion. However, this is colorless because the zinc doesn't have any d subshell, unpaired d subshell electrons. So this just gives you a bit of an idea of the different colors that we can see due to the different oxidation states of the metals, remembering that this will influence how many ligands can come around to the central ion, as well as how close, depending on the charge density of that central metal ion. And that's it. That is the last of our content for periodicity, and I'll see you in class.